Have you ever really stopped to think about how a thought, becomes an action? It all comes down to this incredible high-speed conversation happening inside your head between brain cells. Today, we are pulling back the curtain on the synapse, that tiny, powerful communication bridge that makes literally everything you think, feel, and do possible.
So, let's kick things off with a big puzzle. You've got this electrical signal, right? A nerve impulse zipping down a cell. But here's the catch. These cells, these neurons, they aren't actually touching. There's a tiny physical gap between them. So how in the world does that electrical signal make the leap across empty space to keep the message going?
Well, the answer to that puzzle is a truly amazing piece of biological engineering called the synapse. It's the bridge that solves the whole problem.
Now you can think of the synapse as the universal adapter for your entire nervous system. And we're not just talking about brain cells chatting with each other here. A synapse is how a neuron tells your bicep to flex, or a gland to do its job. It is the fundamental point of connection for, pretty much everything.
And in every single one of these microscopic conversations, there are two main players. You've got the sender, which we call the presynaptic neuron, pre as in it comes before the gap, and then you have the receiver, the postsynaptic neuron. See? It's pretty straightforward. A sender and a receiver.
But here's where things get really interesting. Nature didn't just design one way to build this communication bridge. Nope. It came up with two totally different strategies, and each one has its own unique superpowers.
So let's meet our two contenders. First up, you have the electrical synapse, which is all about raw, direct speed. And then you have the chemical synapse. It's way more common in our brains, but it's also a little more sophisticated.
All right, let's put these two synapse types side by side. What makes them tick? What are the fundamental design differences that make each one so special? Okay, first up, the electrical synapse. Look at this, it's basically hardwired. The two cells are physically connected by these little protein tunnels called gap junctions. This creates a direct pipeline, letting the electrical signal, the ions, flow instantaneously from one cell to the next. It's incredibly fast, which is why you find these in places like your heart, where you need perfect split-second synchronization.
Now, chemical synapses, they play a totally different game. Here, there's that physical gap, the synaptic space. The electrical signal can't jump it. So instead, when the signal arrives, it triggers the release of these tiny chemical messengers called neurotransmitters. These little guys float across the gap, they lock into specific receptors on the other side, and that action is what kicks off a brand new electrical signal in the next cell. It's an amazing conversion of electricity to chemistry, and then right back to electricity.
And this table really just breaks it all down, doesn't it? Electrical synapses, they win the race on speed, hands down. And because they're a direct connection, the signal can actually flow both ways. But look at that last row, flexibility. The chemical synapse might be slower, and it's strictly a one-way street, but it's highly modulable. And believe me, that one word changes everything.
Which of course brings us to the biggest question of all. If speed is so critical for a nervous system, why is our brain, the most complex computer on the planet, built almost entirely out of the slower chemical synapses? Because here's the secret, the most important takeaway. That tiny delay, that chemical step, it isn't a flaw. It's the single most important feature. The slowness is the entire point.
You see, that moment, that little pause where the signal becomes chemical, that's where the magic happens. It creates an opportunity for control. The connection can be turned up or turned down, strengthened or weakened. This is how you learn. Every single time you form a memory or get better at a skill, what's really happening is you're physically fine-tuning those chemical connections. That modulation is the very foundation of complex thought. It's how you grow and change.
So the big idea to take away from all of this is that our brain's incredible power doesn't just come from raw processing speed. It comes from the almost infinite flexibility of its chemical network. Which leaves us with one final, very provocative question to think about. If our thoughts, our memories, our very personalities are all rooted in this delicate chemical balance, what does it really mean when we decide to change the chemistry?